Last week, we talked about the simple regression model, in which we had this relationship between the x variable and the y variable, and the x variable could take on a number of continuous variables. Okay, so for each observation of x, you had an observation of y. Okay, so you had this kind of data set drawn from two continuous variables. In this lecture, we are going to talk about dummy variables, in which the x variable might take on a limited number of values, two values, either 0 or 1, either here or here, right? So in this case, you would get a certain data set which is limited to two values of x. And how can we use this within our ordinary least squares framework? We're going to look into that now. So to get just the idea how this works, we can consider this regression. The wage equals the intercept plus a certain beta 1 times the master dummy variable. So this master variable is either 0 or 1, right? So that means that we have a data frame which is kind of like this, where you have wage and you have the master. Okay, so for example, if we count in euros, the first person that we look at has 52,000 euros in wages and has a master's degree. The second person has a 48,000 wage and does not have a master's degree. And the third person earns 73,000 and does have a master's degree. So the data frame would look something like this, okay? And what we could do is just to run this regression with the dummy variable and get some results. And we are going to show why this is so. We also assume that the OLS assumptions with the expectation of the residuals are equal to 0, given the level of the master's degree dummy variable. So what does that mean? It means that even if master's degree is 0, when master's degree is 0, then the residuals are expected to have a value of 0, okay? Or you expect the mean of the residuals to be 0. Also, if master's degree the master's degree variable is equal to 1, the expected average of the residuals are equal to 1, or are equal to 0, I mean. So in this regression, master, the variable, the dummy variable, is not continuous. Okay, so we can't really think of beta 1 as a slope. because we do not have any values for the master's variable between 0 and 1, and we do not have anything outside of that either. So how could we interpret the coefficients? Well, one thing you can do is to insert the values for this dummy variable, either 0 or 1, and then look at what you get. Okay, so for example, the conditional expectation of wage when master is 0 is just beta naught. Okay, because as you see in the equation, if master is 0, then beta 1 is beta 1 times 0 falls away and becomes 0, and you are left with the beta naught. Okay, so the conditional expectation of wage when master is 0 is just the beta naught. So what we do is that we write this as the expectation of wage given a value of master equals 0 is beta naught. Let's see, I will just remove that one. So this means that the population average among those who do not have a master's degree is beta naught. Okay, and when master's degree is equal to 1, then the conditional expectation is equal to beta naught plus beta 1. So what we do is that we write this as the expectation, the average of wage given master is equal to 1, is beta naught plus beta 1. So the population average among those who have a master's degree is beta naught plus beta 1. So if you take the difference, then you have the beta 1 is the difference between these population averages, and this we can use a lot. So for example, if master equals 1, then the predicted wage, now we're not talking about the population average, but the sample averages, okay, because we have this hat over the coefficients. So if master equal to 1, the predicted wage is beta naught hat plus beta 1 hat. Okay, the sample averages added together, or sample average of no master plus the difference between no master and master. Okay, the sample difference. And for those who do not have a master's degree, the predicted wage is just beta naught hat. So let's see, I can show this kind of graphically. If masters is here and wage is here, then we have 0 and 1, and we have some data, and most of the data is around here. This is the sample average, and likewise you collect data for people with master's degrees, and their wage is here. Then your, in effect, your regression line will go, okay, that was your regression line will go something like this. Okay, these points in the middle here, they are nonsensical because you can't have half a master's degree. And what you have is this is beta naught hat. This is the sample average of those who do not have master's degrees, whereas if we just draw the line here, this is the beta 1 hat, which means the difference between the means. Okay, the sample means, I mean. Okay, so beta naught is the population average wage for those with master equal to 0, and the OLS estimate is the sample average wage among those in the sample with master equal to 0, and the same goes for those who have master equal to 1. That the beta 1 hat is the difference in the sample average wage among those with master equal to 1 versus those with no master degree. So we have gone through this, that beta naught is the sample average of workers without a master's degree, and the sum of the beta naught hat and beta 1 hat is what you expect the wage of a worker with a master's degree to have, and that the beta 1 hat is the difference. And why is this important? Because you have learned previously to compare two means and check if they are different. Well, these dummy variables, they are much more flexible because you can use them to compare one mean versus several other means. For example, if you want to look at house prices in January, are they statistically different from house prices in any other month? Then you can compare the house prices in January with all the other 11 months. In addition, you can compare the difference in slopes, not just level, but slopes. So dummy variables, as we will see later in the course, is massively practical to know about. See you next time.